So this is the title of my presentation, is Simplified Transmission Modeling for the Next Generation Extended Reach Access Coherent Systems. Fortunately, Antonio already introduced some of the main principles, and then this will help me to present the next part of the workshop. Okay, let me set here the pointer. Okay, this is the outline of my presentation. It's divided in 4 parts. The first part is just introducing the network that I am analyzing in this presentation, and then briefly, in a nutshell, the theoretical modeling for this analysis, estimation of the performance of these systems. And then I'm going to present 3 different cases in which we apply this modeling approach and the experimental validation. So this is the structure of an optical network, and in a very, let's say, abstract way, already introduced by Antonio. And the focus of this presentation is on the edge of this network, which is the access part, the final part that arrives to the end user. Currently mostly arriving to residential users, but this can also arrive to mobile transport radio stations, and also to business and universities, or these more larger bandwidth consuming users. Here, as you can see, at the edge of the metro network and the access network, there is the central office, which currently performs this optoelectrical conversion and electronic switching, which is one of the central parts that we will like to avoid if we want to build a more efficient optical network that goes to the edge. But currently, this is the situation. I am going to call this like the current pond scenario. PON arises from passive optical network, so that means that between the central office and the final user, there are no active devices, only passive optical network devices, which are mainly the fiber and the splitters that distributes the traffic into the final users. So, as Antonio mentioned, this is the simplest optoelectrical technique is IMDD, using the on-off keying for modulation format. And this is currently used by these passive optical network technologies. By all generations are based on this technology. And the more recent one is achieving 50 gigabit per second per wavelength. And if we also have the possibility to have 40 gigabits per overall, with 10 gigabits per second per wavelength, which is a WDM PON. But this is the maximum rate. There are already some commercial products of offering this kind of data rate, and it was standardized like 3 or 4 years ago. Something that is special about this kind of networks in comparison to core networks and metro networks is that it operates into a single fiber infrastructure with bidirectional transmission between the upstream and the upstream. Downstream and upstream are sharing the same fiber, but in the current PON scenario, each of them have a different wavelength. So there is no impact on reflections on this architecture, which can be different when we move to another kind of technology, as I am going to speak later. This is a short reach optical network, but it is not exactly the same as for data center leaks, since in this case, the main difference is the optical power budget that have to be supported. In a PON access network, we need at least 29 dB. More frequently, the typical value is 30 dB. And in order to be sure that we can reach all the PON scenarios worldwide, it's around 32 dB of optical power budget between the OLT and the ONU, which is the end user here, in this case, the residential users. So what does that mean? Remember that this is a passive optical network, so there are no active devices here, there are no amplifiers. So this imposes a strong challenge in this kind of networks in order to support this big power budget that, for instance, in data center links, this is less than 10 dB. So the technology is different, and this is one of the reasons why we are still using IMDD and on-off keying, which has the higher sensitivity among different modulation formats. And another challenge here is that at the end user, as Antonio said before, the cost is important. So we should keep this part of the network simple. So due to all these features, it is very challenging to go beyond 100 gigabit per second per wavelength. There are currently some demonstrations that using IMDD, you can reach 100 gigabit per second, but we are at the limit. So if we want to jump from the current 50G to, let's say, 4 times, which is the typical jump in this kind of PON networks, then we will need to go to 200 gigabit per second. And then maybe this technology and this approach will be no longer feasible. One solution that has been discussed is the use of coherent technology in these kind of networks, because it offers higher sensitivity, more tolerance to chromatic dispersion, since this can be compensated by DSP at the receiver side, and it also has higher capacity. But not only this, due to these characteristics, we can enable other kind of benefits that can be explored and are the basis of all this research. So what is this? That since we can achieve more chromatic dispersion compensation, we can achieve longer reach, and then we can start exploring extended reach PON in order to try to merge the access and the metro segments in order to have a more flexible and a more adaptive network that could be all optical, avoiding the optoelectrical conversion at the central offices in the boundary between metro and access. So basically trying to blur these boundaries in the network. Another thing is that we can have higher explicit ratio, so we can have more ONUs per tree, which will help us in order to build more bigger coherent technologies. So this is like the schematic for metro access or extended access network. I will use this terminology during the presentation as synonyms. So basically coherent extended access or metro access will be for this presentation basically the same. And the main let's say feature behind it is to try to, instead of converting to optoelectrical, we will distribute all optically using ROADMs here in the border. And in this way, we can communicate directly from some part here in the metro network directly to the end user. And using coherent technology, we can support ultra high speed users, also the next generation of mobile transport that requires around 100G or more per link, and still also trying to reach this residential user with the cheapest technology, which is one of the main challenges nowadays for the introduction of this technology. As a further technological improvement, if we combine the coherent technology with digital subcarrier multiplexing, already also explained by Antonio, then we can have higher spectral granularity, which offers more network flexibility. And also, as I'm going to explain in the following slides, this allows to use the single fiber bidirectional infrastructure already system for PON worldwide, using a single laser architecture that is the typical transceiver architecture using coherent technologies. So this is another way of showing the full core metro and access optical network. Again, this is the current situation in which we have these switches, electrical ones, that performs the optoelectrical conversion and the routing, distribution, and aggregation. And once we replace by a novel metro access conversion network, then we can reach a given point in the metro. I am just repeating myself in order to be more clear, to an end user. But this introduces a novel network that is not longer just access or just metro long haul. We introduce here a new element in the network, which is the ROADM. that allows for the distribution and aggregation in these kind of networks, but also introduces some impairments, like for instance, the filtering or some PDL. Another characteristic that I am going to show in the next slides is the list of impairments that since we still have the metro access with their own characteristics and their own requirements, we need to offer a high optical power budget in the access link without amplifier in the middle. And then because of that, we have to use a high launch power. In this case, we have impact of fiber nonlinearities, which is non-negligible, that were not present before in a typical access system. Even if it is short reach, due to the high launch power, we have some penalty due to nonlinearities that we have to take into account in the modeling. Another characteristic that was not typical in a typical metro link or long haul system that were always amplified is that here at the receiver side, we arrived with a very reduced power. Here we represent the splitting ratio by a variable optical attenuator. And then at this point here, we have low optical power. In this case, the intrinsic noise of the coherent receiver starts also counting, which I repeat myself, was not the case for the typical metro networks. And then we have also the combination of transceiver noise that is becoming also non-negligible anymore. Due to the use of optical amplification for the metro link, we need to use optical amplification in the metro link part, which was not common in the typical access systems. And then we have to introduce also the impact of the amplified spontaneous emission noise. The optical noise in combination with the transceiver noise makes these kind of systems more interesting and more challenging. Another feature here that I mentioned before is the access links operate in a single fiber infrastructure. And if we want to use a single laser bidirectional transmission, then we introduce here a novel impairment, which is the interference from reflection, which was not typical nor in metro links that normally use dual fibers, one for upstream, one for downstream, let's say. And it was also not common in the access links operated with MDD, in which the upstream was in a different wavelength than the downstream. So this is another novel impairment that we have to take into account in these kind of networks. The other thing is that if we introduce the digital subcarrier multiplexing and using Nyquist optical channels, they are very densely packed. So we start having also some linear crosstalk between them. And last but not least, the use of ROADMs and high-speed transceiver introduce filtering considerations that starts getting some bandwidth reduction and some filtering misalignment between the signal and the filter from the WSS inside this ROADM that also color the noise coming from these amplifiers, which is something that was also not typical for the current system. And then we have a dependency of frequency in the SNR of this kind of system. So when we put all these ingredients together, the normal standard tools in order to analyze this performance estimation that are normally based on the transmission of different PRBS with a long symbols and then bear counting using time domain numerical simulator, that for the nonlinear part of the fiber emulation propagation, you solve the Manakov equation that Antonio also presented, that this is a complex equation that need to be solved by numerical methods like this split step, become very CPU and time consuming. So if we want to avoid this in order to have more still accurate but fast tools for this network, let's say provisioning, dimensioning, design, or analysis, then we need to explore simplified semi-analytical modeling approaches that has a trade-off between sacrificing some physical accuracy, but giving us more fast and still reliable quality of transmission estimation. So this is basically the topic of the next slides. So we are based our approach using the Gaussian noise modeling approach that for coherent optical systems that map completely the electrical field into the electrical signal works properly. And I'm just going to recall this AW channel that is very common in textbook subjects. in which the main characteristic of this channel is that we assume that the noise that is affecting a given digital transmission system is a additive white Gaussian noise variable. And then we can compute what is this metric, the signal to noise ratio, as the ratio between the power of the signal and the power of the noise that I will term as N in the rest of the presentation. And the main feature here that we remember is that since we are modeling the noise as AWGN, then we have analytical expressions to calculate the probability of error or the bit error ratio using this SNR as a metric. So basically, this is the main foundation that is very straightforward. What is like the breakthrough for optical coherent systems when we use this approach? That, for instance, instead of solving the Manakov equation with the split step, we can model the fiber nonlinearity as AWGN as well. And then we consider both the AC noise coming from the amplifiers and also the nonlinear interference noise coming from the fiber nonlinearities, both as Gaussian additive noise. By doing this, we can still use the previous approaches, just generalizing this SNR definition and adding the AC noise and the nonlinear interference from the fiber, and still use these analytical formulas in order to predict the bit error ratio or the Q factor that at the end defines the quality of transmission of the full link. So this very, let's say, breakthrough approach was introduced by different authors, but the more famous one is the group of Pogliolini at Politecnico di Torino. So what we do here, extending this approach, is asking ourselves if we can extend these assumptions in order to introduce more impairments and modeling them as additive white Gaussian noise, or maybe not white. This is an assumption that I remove in the next slide, and produce this kind of generalized SNR with as a sum of very different contributions from assuming all of them are noise. We know that physically they are not Gaussian noise, and some of them they are not actually noise. But for this simplification, we will assume this, and then we will prove experimentally if this assumption is correct. And at the end of the presentation, you will decide if this approach is reliable, accurate, or not. So this is another part that we introduced. Since we introduced ROADMs and transceivers with bandwidth limitations, we need also to extend this idea of the Gaussian noise in order to introduce the frequency dependency. Then we could have transfer functions here coming from the WSS that colors also the noise. And once we start introducing these frequency-dependent impairments, we need an equalizer at the receiver side that was not present before. And we base this initial analysis by assuming that the equalizer that normally is a MIMO LMS equalizer, also presented by Antonio before, we can abstract this kind of equalizer as an ideal minimum mean square error equalizer, in which there are existing theory from the digital communications books. So how we did this? So for instance, I'm going to present just one example. Let's consider an AC noise that I will define as the noise 1 here in this schematic, that could traverse some kind of transfer function that color it itself, but also when we add it to the signal, then it starts like getting filtered by the next part of the propagation elements, for instance, ROADMs, and then it get color. The noise get color. The signal itself also get filtered by these different stages of filtering in this path here. And then when we arrive to this point before the equalizer, we have both the signal frequency dependent and also the noise. And then we can calculate something called the frequency resolve generalized SNR, that is the power of the signal depending on frequency, and also the sum of the different noise contribution that are also frequency dependent. If we extend this concept into the digital subcarrier multiplexing, we can consider each subcarrier as an independent channel, and then each of these will experience a different filtering effects. Let's say, for instance, let's think of a ROADM that has a band pass characteristic. So the edge subcarriers will experience a different filtering than the central ones. And then we have to take into account each of them as independent channels experience different frequency conditions. So the main question here is how to go from this frequency-dependent generalized SNR to a GSNR that we can convert with the analytical standard formulas into bit error ratio. Well, this is done by this formula here that does the magic and is derived in a full chapter of this book here by Robert Fisher. And it could seem like it's a simple formula, but it's a powerful one that requires, yes, I repeat, a full chapter of this book in order to get this. This was developed by Digital Communications in general system, but then we adapted to our optical systems that we are analyzing. So this is the last part of the introduction. What we use as a metric in order to evaluate the performance of the system. And normally the bit error ratio is one of the common metrics or the Q factor, but we consider more useful to use the sensitivity penalty or the OSNR penalty in order to measure the accuracy of our models. So what is the sensitivity penalty? Let's consider here that we have a baseline case in which we have only intrinsic transceiver noise, which is a noise that we cannot get rid of. And then we start changing, for instance, the received optical power in this case, and we compute the bit error ratio that comes from the generalized SNR and produce this curve that is the baseline. We cannot get something better than this. This is the baseline of every transceiver and is something that you can characterize experimentally. And in order to get this point here, that this is the baseline sensitivity at a given bear target. In this example, I choose 10 to minus 2. Then we have a given impairment of the test. It could be reflections, it could be optical noise, it could be filtering, it could be whatever of the impairments that I mentioned before. And then we start getting the performance worse and worse by increasing this impairment and then reducing the SNR associated with this given impairment. And as you can see here at the bed target, we start cutting this, computing these points. And this is what we call the sensitivity penalty. This is the most typical metric in the access networks, because from this and knowing the transceiver power, you can estimate the optical power budget, which is a very important metric in these kind of access networks. For the metro part, the more important metric is the required OSNR penalty, which is exactly the same concept, but instead of varying the power, we vary the OSNR in the system. And then we start also introducing the impairment of their test, getting the system worse and worse and worse. And then we start again calculating the OSNR penalty as compared with the baseline case with only intrinsic transceiver noise, and get exactly the same concept here. So we can use one of the other metric here for our analysis in order to compare against our model and the experiments or simulation work. So, okay. Once introduced here, I'm going to start giving some use case. Okay, I have a question here. Please go ahead.
Since you talked about like the convergence of the metro and access,
yes.
Is there like a single performance KPI that accounts for that combination? Because here you mentioned one for access, one for metro, right?
Yes, one for access, one for metro. Yeah, actually, this adds, as you can start observing, more complexity into the system. There is not yet, because this is a novel topic, yet like a standard or canonical single metric to analyze both scenarios. What we do normally is actually combine both. Then we plot the sensitivity penalty as a function of the OSNR, and then as a third degree of freedom, the impairment on their test. But just presenting this 2D representation of this kind of analysis gives you more like the how we operate or how we measure the penalty in this kind of systems. And then I'm going to present some graphs later in which we actually combine both. Yes. Okay, let me continue. So the first topic that we have analyzed, and I'm going to present part of the work that was presented at OFC and ECO last year by our group, is this single fiber bidirectional transmission. I mentioned before that when you introduce coherent technology in the access segment, then we have the problem that we have to use the same laser in both directions, which causes the problem of we have some reflections coming from the, in this case, for instance, the downstream, that once we reach the receiver and then we have the optical to electrical conversion, this is beaten with the upstream since they both share the same wavelength. And then we have an extra interference coming from this reflection from the other direction. So, but using this digital subcarrier technology, we can avoid this, still using the single laser approach by just interleaving the subcarriers in both directions. As you can see here, we sent half of the digital subcarriers in one direction and half of the other. And then it's like having two different wavelengths in the practice, but in terms of the transceiver, we still use only one optical laser in both directions. And this is something that has been already tested by the former Infinera, now Nokia transceivers, and it works very well. But the question here that we have introduced is what happens if we don't, let's say, waste this bandwidth here, and then we send the full spectrum in both directions, and then we allow having reflections. We need to measure what happened, and then we develop a model, and then we verify it against experiments. So this is the picture here. When we have reflection in single carrier or in digital subcarrier, we can consider this, and this is a part of the modeling assumptions that I introduced in the first part of the presentation, that these reflections inside the bandwidth can be considered as additive white Gaussian noise. Even if they are shaped, we just consider that it is flat enough in order to be considered as AWGN, and then we apply the same theoretical modeling that we introduced before. So all this SNR contribution that doesn't depend on the received power, because in this study we were using sensitivity penalty as a metric, then we wanted to change the received power. We grouped as a baseline SNR that we call here SNR 0. And then the ones that coming from the receiver noise, we approximated as be linearly dependent or proportional to the received power, which is, let's say, a reasonable assumption, since we can just consider that the receiver noise is constant over the bandwidth of interest. And then we can start observing what could be the penalty of introducing the reflection. So without reflections, with what we call the situation, the baseline situation to compare the penalty, we just have the baseline SNR, the SNR arriving from the receiver, intrinsic receiver noise, which can be converted into this expression, just introducing some proportionality factor that is the flat noise, multiplied by the power of the receiver, that we call it sensitivity when it gets the generalized SNR considered as the target one that provides the bare target that we mentioned before. Then when we introduce the reflections here, in order to get the same target performance, then we have to introduce an extra power here that we call the sensitivity penalty. Just doing some algebra, we can arrive to a sensitivity penalty model that take into account the reflections and the sensitivity power, let's say. We tested in this experimental test bed that we performed together with Ericsson at the labs in Italy, in which we use two coherent transceivers. In this case, we explore both single carrier transceivers and digital subcarrier multiplexing transceivers, emulating as a single fiber bidirectional transmission. That's why we have to introduce these circulators in order to distribute the transceiver and receiver lanes at this, let's say, end site. But in the fiber, we have a single fiber transmission for both directions. In order to introduce some discrete reflections, we use this artifact here that part of the power here is mirrored in order to get reflected here, which is that we call discrete reflections and are completely under our control by this variable optical attenuator. We control the amount of reflections here, while the fiber itself introduces some fiber reflections that we call distributed reflections coming from the Rayleigh-Bach scattering effect. So we tested all these different situations, only discrete reflections, only distributed reflections, and the combination of both the distributed reflections coming from 15 kilometers of fiber and discrete reflections controlled by ourselves by means of controlling the power. We tested these different cases, the single carrier and the full mode digital subcarrier with reflections, and also the half mode that I presented before, just to confirm that in this case, we don't have any penalty. So we plotted here the power penalty as a function of one of the, in this case, the impairment of on their test is the reflections, and then we plotted the reflections ratio, and we verified all these markers are the experimental combination of scenarios tested, while the dotted curves are the modeling that using the previous formula derived with these assumptions. As you can see here, we have a good agreement between the experiments and the modeling. So we can say that among these conditions, from this signal to reflection ratio, analyzed here, which are typical values that we can find in a real network, we have a good agreement using this assumption. We also explore the case in which we vary the fiber length, and we just avoid using introducing discrete reflections. So we just have, in this case, the reflections coming from the fiber itself, which are reflections that we cannot avoid. The discrete reflections, maybe we can avoid by using angle connectors, by using the fibers cleaned, and by being careful with the setup. But the distributed reflections, they are unavoidable. So they present like the fundamental limitation itself in terms of reflections. And again, here the markers here are the experimental points, and the solid lines are the model predictions. By modeling the Rayleigh-Bach scattering in this way, this is a formula that was presented in one of a paper before by Politecnico di Torino, and that was also derived using some papers by the 80s and 90s that we also found recently. So again, let's say the key take message is that the model works with these assumptions and with these simplified formulas. And in this case, we don't have even any alternative if we want to use time domain numerical simulation, because there is no canonical time domain simulator in order to predict these kind of formulas. That's why we just compare against experiments. So let's move to the second topic, which is the impact of the filtering in this kind of digital subcarrier systems for metro access networks. These are the model assumptions. The first of them is that each of the subcarriers in a digital subcarrier system act as a single independent channel that then observes a different filtering depending on their relative position to the filter. For instance, an edge subcarrier will experience a very strong filtering here, coming from this very shape characteristic at the edge of the filter, while a central subcarrier here will see a flat filtering. So this is one of the assumptions of the two assumptions of the model. The third one is that we also introduce the impact of crosstalk. We just consider the neighbor subcarriers as a Gaussian noise shaped by the pole shaping characteristic of these subcarriers, and then this noise that is here is the one that we consider as a crosstalk noise, also assumed to be a Gaussian additive noise, but this is not white anymore because this is shaped by this pole shaping function here. Regarding the noises, the AC noise, we model it as also as a color noise that is filtered by the receiver transfer function that is inside the electrical transceiver. And the intrinsic transceiver, we model it as a part that is just a constant noise, and a part that depends also on the transmitted power of the signal, which is an intrinsic power-dependent noise. Once we put all these elements together, we have this equation describing the SNR as a function of the frequency and also for different subcarriers. And then we translate it into an SNR that can be converted into bit ratio by this equation that I shown before. So these are some kind of analysis in which we compare the model that are the solid lines, sorry, the marker lines against the simulations that are the solid or dashed lines. And as you can see here, we have a very good agreement, both when we change the impact of the bandwidth, we change different bandwidths. For instance, these are narrow bandwidths. Since we are transmitted at 64 gigahertz, we are operating with 90% or 80% of the bandwidth of the signal. And we also show for different subcarriers. As you can see here, the center one is not affected at all if we have enough OSNR here, while the difference in vertical axis is due to this filter impact. And the most affected one, as you can see here, are the digital subcarrier number 16, that is one of the edge subcarriers. So the agreement is good. And coming back from the previous question here, we plot both sensitivity penalty that accounts from the received power in the access segment and the OSNR that accounts from the metro part of the impairments. So we did repeat the same by analyzing the impact of the crosstalk. How did we increase the crosstalk? By increasing what we call the roll-off factor of the transceiver shape, of each of the transceiver shapes. That basically the higher this roll-off factor is, the wider becomes the shape of the filters, and then the higher the crosstalk. And again, we observe a good agreement by our assumption that this crosstalk can be considered as a filter Gaussian noise by comparing these markers and solid graphs. We did another step beyond comparing this in a transceiver, in an experimental emulation using real-time transceivers. In this case, one from Ferrera, now Nokia, with 16 subcarriers with the same characteristics as Antonio talked in his before. So for instance, here we present just for graphical representation of the experimental effects of filtering that we perform by using this device that is a wave shaper, in which it is possible to program any transceiver, well, almost any filtering shape. And in this case, we use a super Gaussian filter with a bandwidth of 64 gigahertz, while the bandwidth of the signal is 64. So 54 is around 80%, with an order 3, which is a steep bandwidth emulating the cascading of different row DMs. And then it is very evident that the edge subcarriers suffer for this filtering, while the central ones not. And then we wanted to analyze that our model still predicts well the experimental results. And this is something that we will present at OFC in 2 weeks. And these are the results. The marker are the experimental result. The solid lines are, again, the model predictions. And as you can see here, for different subcarriers and for different combination of bandwidths, we have a good agreement. So let me go to the last point that is going to be the shortest one, because this work hasn't been still published. Actually hasn't been even accepted, but we will submit to this ECOC conference that will happen in Denmark, and also to part of this analysis will be presented in this summer topical. My colleague here, Giuseppe Parisi from the group, is the one that is more devoted to this nonlinear analysis, so I'm going to be brief. So again, let's go back to the typical formula that we use, and then we will focus on this nonlinear noise that can be modeled in this way as a SNR coming from nonlinear interference. From Pogiolini's papers, we have this expression here in which the SNR is modeled as the inverse of the square of the power multiplied by this factor that is the one that do the work in order to model the nonlinear interference. So this one can be computed using different approaches, different flavors of the Gaussian noise for fiber nonlinearities. There is the typical Gaussian noise that is inside the GMPY, for instance, tool, that it is effective if we have large symbols and large amount of dispersion and a large number of channels. Typically, this is the case for long-reach systems, WDM systems. But once we start moving to short reach, we don't know if this is still effective. There are another approximations, for instance, like the incoherent Gaussian noise, that is a simplifying version of the Gaussian noise that can derive some close analytical expressions. And the last one is what is called extended Gaussian noise, that corrects from one of the assumptions from the original Gaussian noise, in which they consider that the signal is Gaussian itself, that can be modeled also as a AWGN channel. In this extended Gaussian noise model, we don't have this limitation anymore. And this is important because, as I am going to show now, for short reach, we don't fulfill this Gaussian signal assumption. The drawback of this model is that it's computational more strict, demanding than the GN. But one solution that here my colleague explored is to use the Monte Carlo integration technique in order to solve all these triple integrals that are required in order to implement this model. So as I said before, for instance, let's say this is a transmitted constellation, 16 QAM, that after 14 kilometer different spans of single mode fiber, and given this 32 gigabaud that gives you around 200 gigabit per second if we are using QPSK. At the output of this span, we have basically a Gaussian distribution. And then the GN model is effective. In this case, since we have high accumulated dispersion and high symbol rate per channel, the four-way mixing effect is negligible, while the XPM, that is basically phase noise, is dominant. And also, in this case, we have closed form solutions available also for the EGN. Unfortunately, for the short reach scenario, as you can see here, the constellation at the output is not Gaussian anymore, doesn't look like Gaussian noise. Also, we have lower symbol rate per subcarrier, lower accumulated dispersion. We are talking about links that are 20 kilometers, 40 kilometers for the extended reach, and less than 100 kilometer average, even considering the metro access link. In this case, four-way mixing is relevant since we have very low rate, and we use subcarrier multiplexing. All these channels are densely packed together. And then the question here is if GN or EGN models are still suitable for analyzing these. So let me conclude this talk. We have developed this simplified semi-analytical model in order to predict the performance coming from these digital subcarrier and metro access networks. It is not that, as the physics joke, as assuming a spherical cow, that we consider that this is just AWGN everything, but instead we start like simplifying from a different, let's say, a complex situation in which some of the effects can be neglected in order to arrive a simplified model that still comprehend the relevant effects as I have shown in the comparison between simulations and also between experiments. It is not said that this is the, let's say, the ultimate solution, but is accurate enough in the cases that we are analyzing. For sure, there are some limitations that we are continue exploring. We have also tested experimentally the accuracy of our model in some particular conditions, but up to now we have analyzed each impairment independently, separately. So our next steps is just to test this model in more extended scenarios in which we can join different impairments, for instance, the filtering, the nonlinearity, the bidirectional transmission, and in this case, emulate a realistic full network link. And we also, the next also final step or the final goal is to include this model in a physical aware networking tools for design provisioning or just prediction in real time, since they are mostly fast models coming from semi-analytical solutions. So yeah, thank you for your patience, and thank you very much for your attention.